In the previous class, we have seen the concept of graphs, right? So, what is a graph? It's a collection of vertices and edges, right? And also, we have discussed various kind of terminologies, right? What are the terminologies that we have discussed? I mean, we can say them as what is a vertex, what is an edge, right, etc. Various kind of things that we have discussed. In addition to that, we have seen what are the various types of graphs, right? So what are the various types of graphs we have seen? Weighted graph, unweighted graph, directed graph, undirected graph, directed acyclic graph, what is biconnected component, etc. Various kind of things that we have seen. In addition to all these, we have seen how to represent the graphs, right? So in general, as a human being, we can able to visualize a particular graph, right? But how the system will understood or how the system will store the graphs in the system, right? For that, we have seen various representations of graphs. We have seen the old way of representation, that is edge list representation. This is generally how the old structure they are following. Nowadays, commonly they are following, one is adjacency matrix representation. Adjacency matrix representation. The another one will be adjacency list representation. And also we have seen the basic differences between the both of them, right? So if you look into the differences, adjacency matrix is preferable when you go with the concept of finding whether two nodes are connected or not. Whether two nodes are connected or not, we can go with the adjacency matrix representation. This is how it is efficient one. If you want to find out what are the adjacent nodes, what are the adjacent nodes of a node, we can go with the adjacency list representation. Node of a node, right? In general, we can go with anything, but specifically when you decide with a particular task, then you can go with the specific things, right? So what is the drawback that you observe in the adjacency matrix? Space complexity, right? So in the adjacency matrix, you have observed the space complexity as big O of V square, because it's having, you are making use of, even when there is no edge, you are making an indication as 0. It is a kind of wastage of memory. Instead of that, why can't we left out with zeros, and why can't we allocate space for only the edges which are connected? That is how you can reduce the space in the adjacency list, right? Fine. So this is what we discussed in the earlier classes. Now in today's class, we'll go with various kind of graph traversal mechanisms. Have you anywhere observed traversal mechanisms? Right? Very good. You have observed the traversal mechanisms in the trees, right? So in the trees, we have seen various kind of tree traversal mechanisms. What are the various kind of tree traversal mechanisms are they? One will be pre-order, in-order, post-order, which are very, very important for the gate up, right? So pre-order means how we will do? We are going to first print the node. We can say it as head, then we'll move to the left, then we'll move to the right. Similarly for in order, we'll go for left, then print, then go for right. Post order, left, right, and right. Suppose for here we have various kind of tree traversal mechanisms are there. Why can't we use these three mechanisms in the graph traversals also? Right? So it couldn't possible to use the same traversal mechanisms in graphs. The simple reason is graphs are purely different from trees, right? Why? Because if you look into the tree, in general, tree traversal mechanisms always going to start with one particular node, that is root node, right? We are going to start with the root node. and we will follow specific kind of mechanism where it might be a pre-order, in order, or it will be the post order. But if you go with the graph, is there any root node? There is no root node, right? Which means that you can start from any vertex. At that situation, the existing tree traversal mechanisms are not suitable for graph traversal mechanisms, right? So that's why they come up with a new concept called graph traversal mechanisms. Okay, fine. So have you understood the reason why they are moving for the various kind of specific graph traversal mechanisms, right? Fine. So there is no root node, right? That's the reason they come up with two kind of mechanisms. One will be breadth first search traversal mechanism, and another one will be depth first search traversal mechanisms. We can simply call them as BFS and DFS. Okay, so if you look into one by one in depth about it, first let us go with the BFS, breadth first search travel mechanism. So how it will do now? When you look into any kind of a graph, first we are going to be at a particular node. Let's say this is a kind of a graph. Let us assume that 1, 2, 3, 4. Now is it a graph or a tree? Graph, right? I am extending with some other nodes, 7 and 8. Fine. Now if it is a tree, we can able to easily identify the what is the root node. If you know the root node, we can apply various kind of tree traversal mechanisms. But as it is a graph, there is no root node. So what is the first thing you require? You have to mention what is the root node or what is the starting node. You have to mention what is the starting node. So what you have to take as a starting node? Can we take anything? Yes, we can take anything as a starting node. So now one I can represent as current visiting node. Okay, which means that you are at the node 1. How BFS will work? BFS will try to perform breadth-wise traversal, or I can say it as level-wise traversal. Have you able to understood where are the levels? Is there any levels? Have you able to identify? Right? In general, you might not understood because it's a kind of graph. It is spread over the whole the paper, right? So suppose for example, if I mention something like this: 1, 2, 3, 4, 5, 6, 7, and it will be 8. Is it a graph or tree? Now it is also a kind of a graph, but as per the representation, you can able to understood what are the levels here, right? So which means that there is no need to identify the levels once you are able to understand the solution. For the sake of our understandability, I have mentioned the graph something like this. First, what it will do BFS, if you are at a particular node like 1, it will try to visit all the adjacent nodes. In a level by level fashion. Means once you are able to understood a node as the current node, it is going to identify or it is going to first complete visit the adjacent nodes. In the current level. It will visit the adjacent nodes of the current level. Once the current level is completed, then it will move to the next level of adjacent nodes. This is how BFS will work, right? So in order to implement this concept, the BFS algorithm internally uses a data structure called queue. How the queue is able to helpful for you means they will able to identify simply the adjacent nodes of a particular node. how it will means. Suppose for example, I started with the node 1. I started with node 1, right? So if I started with node 1, this is a kind of queue. Let me assume, right? So it's having how many nodes are there? 8 nodes are there, which can start with index 0, 1, 2, 3, 4, 5, 6, 7. Now my first node is what? 1. I added into the queue. I added into the queue. Then what are the nodes that I have to visit next? Adjacent node to the 1. What are the adjacent nodes which are to the 1, 2 and 3, right? That we need to remember. So to remember that, they are going to be added. See, I am going to look into the figure gem. I am explaining for the figure gem. So this is, let me say that for figure K. What are the adjacent nodes of 1, 2 and 3? Because 2 is connected to 1 and 3 is connected to 1. So I can say them as 2 and 3 are the adjacent nodes of 1. Fine. So I explored 1 for you, which means that initially I started with the vertex 1 and identified the adjacent nodes of 1 are 2 and 3. So I am going to explore them. Right? Once 1 is completed, I will go with the next visiting vertex. What is the next visiting vertex? 2. You have to visit all the adjacent nodes of the current level. Then you have to move to the next level of adjacent node. So I will go with the 2. While visiting the nodes adjacent nodes of 2, what are adjacent nodes of 2? 4 and 1. 4 and 1, right? But you should not include 1. The reason is 1 is already visited. Can I add 4 here? Why I have added 4 here? Because 4 has to be visited after visiting 2 and 3. After visiting 2 and 3 only I have to add. That's why I have added to the queue. Which means that 4 should be visited after completing 2 and 3. Right? Now 2 is complete, which means 2 is connected with 4. Now check about the next one, 3. What are adjacent nodes of 3? 1, 4 and 5. 1 is already covered. 4 is already added into the 4 is already trying to cover by some other node. Next 5 should be the adjacent one. Right? So from 3 I can cover 5. Right? Next 4. What are the adjacent nodes of 4? 2 and 3. They are covered by already someone. So I no need to add the path. And next I will go with 5. What are adjacent nodes of 5? 3, 6 and 8. Right? Do I need to add 3? No, which is already covered. Next I will add 6 and 8. You might get question. Can I add 8 and 6? Yes, you can add in any order. Which means that if you go with performing the BFS operation, you can get multiple BFS orders. There won't be any inequal path for you. Right? Fine. So now we are at 6, I think. Right? So 5 to 6 you have to add and 5 to 8 you have to take care of. Next I will go with 6. What are the adjacent nodes of 6? 5 and 7. 5 is already covered. 7. Right? So from 6 you have to add 7 to the queue as well as to the graph. 7 is done. Next I will go with the 8. When I am exploring the 8 vertices, what are the 8 adjacent vertices? 5 and 7. 5 and 7 already covered by someone. So I won't add anything to the edge from 8. Next 7. What are adjacent nodes of 7? 6 and 8, which are already covered by someone. So I won't add any vertices extra edges to this graph. Right? So this is how BFS is going to work for you. So what is the final BFS order? One BFS order will be, one thing will be 1, 2, 3. See, this is how, right? You have visited the nodes. 1, 2, 3, 4, 5, 6, 8, 7. Similarly, can you able to guess what might be the other order? Can we do with something with other way? 1, 1. From 1, can I visit 3? Can I visit 2? and from 3 I can visit 4, 4, from 3 can I visit 5, from 5 can I visit 8, can I visit 6, can I visit 7? Yes, this is one more possible of BFS order. What may be the other possibility of BFS order? 1, 2, 3, 4, 5, 8, 6, 7. What may be the other possible order? 1, 3, 2, 4, 5, I think 8, 6, 7. Sorry. Good. You are too fast. 6, 8, 7. Like that, you can able to get multiple BFS orders for you. Okay, now. So you won't get any kind of inequal path when you go with the graph. Right? So why you are why you are seeing this concept? It is just meant for to cover all the nodes. That's it. Right? Whether you are able to reach to all the nodes or not, we'll go with the concept of BFS. And based on that, we will have various kind of applications are there that we'll see in the next class. I mean, once we are able to view a particular concept, we are going to have many advantages. Traversing a graph is nothing but traversing some kind of real world problem, something like Google Maps, finding the shortest path, finding whether the entire graph is connected or not. All those are all various kind of applications are there that we'll see in the next class, right? So similarly, can you give BFS order for the figure K? If the starting node is 1, the starting node is 1, can I go with 1? Yes or no? Then can I go with 2 and 3, 4, 5, 6, 7 and 8? What will the resultant graph? 1, 2, 3, 4, 5, 6, 7, and from 4 you are going to get be connected. That's it. And you won't get anything, any other things. Okay, na? Fine. This is how you have to solve the BFS orders. So now we have seen the graphs are of various types, right? One can be either a directed or an undirected. So far we have seen BFS with undirected graphs. Undirected graph, right? Now let us see a simple example, BFS with directed graphs. Let's see, the graph look like this. 1 can be directed to, reach it to 2, and it will be connected to, let's say, 4, and it's having a kind of a loop, and it will be connected to 3, it will be connected something like this. So for example, this is, let's say, figure L. Now can you say what is the BFS order for the L diagram? Right? So try to do it with the queuing approach, right? So if it is a kind of gate examination, you can solve by yourself, but when you go with any kind of theory examination, you have to solve in the step by step fashion, right? So first I will go with the, so you need to know what is the starting vertex, right? Let us assume that the starting vertex is 1. Okay, if the starting vertex is 1, you have to identify what are the adjacent nodes. What are the adjacent nodes? 2. Can I add 3? No, right? So 3 is not adjacent to 1. The reason is it is a kind of directed graph. Earlier it used to be something like this, 2 to 4, something like this, right? So 2 is adjacent to 4, 4 is adjacent to 2. Suppose for example, if it is having some arrow like this, 4 is adjacent to 2, but it is not adjacent to 4 because we are unable to reach from the respective node. So 1, if I start with 1, the adjacent nodes of 1 are only 2, only 2. Then from 2 you are visiting, what are adjacent nodes of 2? 3 and 4, good, 3 and 4. So I have completed 2. Now what are adjacent nodes of 3? 1, which is already covered. Next, what are adjacent nodes of 4? 2, which is already covered. It's already covered. So the BFS order for the given graph will be 1, 2, 3, 4, or it can be, I think, 1, 2, 4, 3. Can I write 1, 2, 4, 3 or not? Because the adjacent nodes of 2 are 4 and 3. So I can go with either 4 or 3. So that's why you got two possibilities, right? So this concept is especially important in the gate where you have multiple answers you are going to get. This concept they will combine with the probability and statistics. How many possibilities you are going to get, like that they may ask. Fine. So this is how you will solve the BFS order for a particular graph. Now let us see how you will do depth first search approach. DFS order of a particular graph. Let us do with the same kind of example what you have taken with BFS. Six, it will be, I think, 7 and 8, and one more diagram I have taken as something like this. Okay, fine. So let me call this as, right. Now what is the meaning of DFS traversal, DFS order? So which means that earlier we are going to start visiting or exploring the nodes in an adjacent fashion. Now we are trying to explore the nodes towards the downside. Explore the nodes towards downside until it reaches end node, or until it reaches any visiting node. Have you understood any this statement? We are going to start with a particular node, like let's say 1, a node like 1, and we are going to identify what are the various kind of adjacent nodes. Out of all those adjacent nodes, we will select one node, like let us assume that 2, and then we will move downwards like that only continuously. Then from 2 to, what are adjacent nodes of 2? 4 and 5, but we will select one node, and after selecting the node, one node, I will move again to the depth, right. I have explored 8. From 8 I can move to either 4 or 5 or 6 or 7, but if you go with 4, which is already visited, so I won't select this part, I will go with 5. If I go with 5, is it visited or unvisited? Unvisited. Now it has done its visiting. Now can I go depth again? I can go to 2, but 2 is already visited, right. I mentioned here you have to move until it has reached the visiting node, or it reaches the end of the graph. I have visited, so what I will do now? I will get backtrack. What is the meaning of backtrack? Once if I am unable to move to the further, I will get back. That is what backtracking means, right. As I already observed a visiting node, I will get backtrack, and I will try to visit further to the next unvisited nodes. What are the next unvisited nodes? 6. I will continue this process to the 3 unvisited. From 3, can I move to 1? No, because it is visited. Even if you try to move to 1, you will move and you can get back, because it is backtracking approach. I will try to visit 7, which is unvisited. Get back 7. And 7, it is unvisited, so make it visited. 7 to 8, visited. So I will get back. Now again do the process getting back until I reaches back to the again first. This is how DFS will work. See, at the end of the both BFS and the DFS, the target is to visit every node perfectly without leaving any node. You have to cover all the nodes. How we are going to cover all the nodes? You can cover something like a spreading from one point to all other nodes. That is what depth by level, or you can start from one point, you can make it connected to the end level, and you can come back again. That is what DFS is saying. Try to apply the same concept for the figure J. Let me start with 1. If I start with 1, What are the adjacent nodes of 1? 2 and 3. I can just simply go with any one of the nodes selecting. From 2, I will go with any one of the adjacent node. What is any one of the adjacent node? 4. From 4, I will go with any one of the adjacent node which is unvisited, 3. From 3, I can go with any one of the unvisited node, 5. From 5, I can go with any one of the unvisited node, 8. From 8, 7, then 6. From 6, I will try to visit any one of the unvisited node. Is any one of the unvisited node? No. I will get backtrack. From 7, any one of the unvisited node? No. I will get backtrack. From 8, is there any one of the unvisited node? No. Get backtrack. From 5, is there any one of the unvisited node? No. So from here I will get backtrack. From 3, is there any one of the unvisited node? No. So like that, it has to get backtrack until again it reaches to the starting node. So why it is getting backtrack? It is trying to cross check whether there are any paths we missed or not. Right. So this is how DFS algorithm will work. Right. In order to implement this concept, in general, what concept we will follow? We will follow the data structure called stack. Right. So let us try to solve the same question with the stack approach. Right. So what we can do now? I can make a note as starting node as 1. Starting node as 1. I am going to take a stack. This is actually a stack, right? We can write either vertical or you can go with horizontal, no problem. So what is the first vertex that we are working? Vertex 1. Vertex 1, right? For the vertex 1, you have to identify the adjacent node. What are the adjacent nodes of the vertex 1? 2 and 3. 2 and 3. Out of these 2 and 3 vertices, you can go with either any one of the things, right? So I will try to select 2. I will try to select 2. I will go with the 2. What are the vertices that are adjacent to 2? 1 and 4. Try to observe. I will just make a note of it for the sake of our understanding. 1 and 4. But if you observe the earlier stack, 1 is already covered, so I won't select this one again. I will go with 4. I will go with 4. Now what is the next visiting vertex? 4. From 4, what are the adjacent vertices? 2 and 3. 2 and 3. Look into the stack. 2 is already covered, so I won't select. 3 is covered or not covered? Not covered, right? So I will go with, see, earlier we mentioned 3 as the vertex that we need to visit, but we haven't unvisited. That's why here we are trying to go with 3. 3. So for the vertex 3, what are adjacent nodes? 1, 4, right? 1, 4, yeah, good. 1, 4 and 5. So I think 1 is covered, 4 is covered, and you have to go with the vertex 5. What are the visiting nodes of vertex 5? 3, 6 and 8. 3 is already visited, 6 I think we haven't yet visited, so I will go with 6. Vertex 6. What are adjacent nodes of vertex 6? 5 and 7. 5 is already covered, so we will go with 7. We will go with 7. What are adjacent nodes of 7? 6 and 8. 6 is already covered. I will explore with vertex 8. What are adjacent nodes of 8? 5, 7, which are already covered, I think, right? As I did all the things in the vertex 8 and there are no adjacent nodes which need to be covered. Try to observe here. Both are cross mark, right? As all the nodes are covered adjacent to 8, which I should not cover any other further. So I will get back. This is what we call as backtracking. I will get back. Now, is there any other nodes that I need to cover from 7? No. I will get backtrack. Is there any other nodes that I need to cover? No. That I will get backtrack. Now, there is a node which I need to cover here, that is 8. But if you look into the diagram, which is already covered by someone. So 8 is covered, so I can make it note as covered and I will get back. all are covered, I will get back. All are covered, get back. All are covered, I will get back. And 3 is unvisited actually. I mean, what are the meanings of 1? I can move from 1 to 3. But if you look into the diagram, 3 is already covered by someone. So I can make a note of it as covered and I will get back. As the stack is completed, I can say that this is the order in which your nodes are visited for you. Right? What is the respective order? So you can make a note of all the things. So the order is something like this: 1, 2, 4, 3, 5, 6, 7 and 8. This is the only order that you will get? No, you will get many different orders, right? So let's say, let me try to write one more order. 1 can start with 3. Can I start with 5? You can start with any order. There won't be any problem. You have to go in depth about it. So 1, 3, 5, 6, 7, 8. Then can I get 2 or 4? Definitely you need to get 4 only. You can't get 4. Sorry, 2. Why? Because from 3 you cannot directly jump to 2. So definitely you have to go with exploring the unvisited node, that is 4 and 2. This is how you can solve the DFS order for a particular problem, right? Similarly, for this, what is the output that you might get? Right, I will try to write one simple thing. Can I go with 1, 2, 4, 8, 5, backtrack, 6, 3 and 7. Okay, now fine. Similarly, I can extend the same problem to DFS for this particular problem. Right? So DFS with the unweighted, like directed as well as undirected. Right? We have seen undirected. Let us go with directed graph. In this directed graph, can you tell me if it starts with 1? If it starts with 1, so 1, 2, 2, 2. From 2 to you can go with 3. From 3 you cannot move further because it is already covered. So I will get backtrack to 2. From 2 I will go for 4. Or you can do something like 1, 2, 2, 2 and 4 and then 3. These are the only 2 possibilities I think you will get if it starts with 1. If it starts with 2, you might get different solutions again. Okay, fine. So have you understood these 2 traversal mechanisms, DFS and BFS, right? So the internal data structure what we are using for the BFS is Q, and the internal data structure for the depth first search is stack, right? Fine. Now let's see the coding part for BFS, right? So in general, how we are going to represent the graphs? We can go with either adjacency matrix representation, or you can go with the adjacency list representation, right? So and one more thing will be the visual representation, which is meant for the human purpose. If you look into this particular thing, BFS of a particular graph, so this is a kind of directed graph. So I think you might understood. There are arrows for each and every node. So we can call it as a directed graph. And this is a kind of a logical representation, or I can call it as visual representation. And for the same diagram, if you want to look into adjacency matrix representation, I can just have a overview look into this one. This is how you will represent the adjacency matrix for the earlier visual representation. And for the same thing, you can go with the adjacency list representation. This is how you will get. Right? These are the 2 representations that we have seen in the earlier class. Fine. Now what I will do now? I will just simply show for you with an animation where I am trying to select starting node as, let's see, 3. Starting node as 3, right? So then it will perform various kind of operations, something like modifying the parent array and the visited array. You might not understood. If I am able to explain with an example, you can get the clear idea. for the time being, just try to visualize into this particular picture. I am trying to click on run BFS. Why it has stopped? What happened? Right? If you are able to understand, here the arrow will be, it's a kind of up arrow, right? Which means I cannot able to move from 5 to forward, right? That's why you cannot able to reach. So the DFS order, sorry, the BFS order for this graph will be only 3, 5. That's it. Have you understood? Fine. So suppose for example, let's select a new graph, and where the starting vertex will be, let us assume that 1, right? Now let us see how it will done. 1 to 0, and then 1 to 6, then 0 to 3, 0 to 4, 6 to 2, 6 to 5, 6 to 7, and then 3 to 7. So you can able to observe on the left side part, the queue is modifying. Right? They are updating the parent matrix or parent array and the visitor array. Okay, so this is the final BFS order for the given graph, right? All the blue color line represents how they have visited the graph, right? So if you look into this particular thing, how we are going to implement it? In general, for the sake of our simplicity, I can go with the adjacency matrix representation. Adjacency matrix representation. In adjacency matrix representation, how we are going to represent? How we are going to create the memory? If I have 5 nodes, it will be of type 5 by 5 matrix. If I have 10 nodes, it will be of type 10 by 10 matrix, right? So for example, I am assuming that there are 5 nodes are there. Each node can be 0 to 1, 2, 3, let us say 4, and it will be something like this. These are the 5 nodes. Then for this, you have to give up with the BFS order, and you have to give up with the DFS order, right? So before getting the solution to write the program, what is the need that you have to know? You have to store how the graph is, right? For that reason, you have to have a kind of two-dimensional array. Two-dimensional array. That array name is something like I am making it as a graph of some max by max, right? I have taken some two-dimensional matrix, right? And I have written all the values where 1 represents an edge that we have seen in the earlier class, and 0 represents there is no edge. Hope you know how to write the adjacency matrix for the given graph, right? You can able to write. Then you have to know one more thing. What is that? What is the starting vertex of the graph? Starting vertex of the graph you have to identify. Once you are able to know what is the adjacency matrix and which represents the edge, which represents the no edge, and what is the starting vertex of a graph, you can able to give solution. You can able to give the solution. How your solution will be, right? So you are using internally queue concept, where you are following let me say DQ as well as NQ. Am I right or not? NQ is nothing but adding the data into the queue, and DQ is nothing but let me say okay, fine, it will be a kind of thing deleting the data from the queue. So in general, while solving any kind of an example, what you did, you are going to select a node. Let's say you are going to select a node 0 that you have added into the queue, which means for the first time, whenever user says for you this is the starting node, what you will do blindly, you can add it into the queue. I mean, you can call for the NQ operation. and you can make it as a visited. Is it visited or not? Right? So in order to make that, I have taken one more an array called visited array. We'll take that. We'll take that, and let's say this is 0, 1, 2, 3, and 4. So what is the 0? This meaning represents 0 represents 0th node is the visiting node, and this one represents with respect to 1, something like that. Now visited of 0, is it visited or not? Yes. If it is visited, I will make them as 0. Right? By default, all are unvisited. Is it all are unvisited or not? By default, all are unvisited. Now, whenever user wishes to add it as a visited, I will make them as 1. Right? So far, we started with the 0 as the starting node, and we assumed that this is a visiting node as so that's the reason I made it as 1. Now, what is the current node? Where we are at the currently? We are currently at the 0. We are currently at 0, right? Which means I have to explore the nodes of 0. I have to explore the adjacent nodes of 0. So what I will do? I will dequeue the 0, and I will explore all the adjacent nodes of 0. Explore all the adjacent nodes of 0. Right? I am going to explore all the adjacents of node 0. How we will explore all the adjacent nodes of 0? In a matrix representation, I will go to the 0th row. I will go to the 0th row, and here we have 5 columns are there. 5 columns are there, where every column is supposed to fill with either 0 or 1. Right? So I think for this graph, for the 0th row, how it will be filled? 0 to 0 is there any connection? No. 0 to 1 connection is there. 0 to 2 connection is there. 0 to 3 no connection. 0 to 4 no connection. There won't be any connection. So how will explore all the nodes of 0 after dequeuing the current element? I will traverse this particular row. And I will take out the element by element. I mean, how I will do that? Let's say this is the kind of matrix graph. So graph of what is the current node? Cn of I will try to iterate this particular value I from 0 to number of vertices called v. So which means what? 0 to 0, 0 to 1, 0 1, 0 2, 0 3, 0 4. Like this is going to select all the things. When these are matched with 1. What is the meaning of this one? There is an edge between 0 and its corresponding nodes. When I have to add it into the DQ, or when I have to add it to the queue, if it is unvisited, how will identify whether it is visited or unvisited? In the visited array, you already mentioned whether it is visited or not, unvisited, right? Suppose for example, the simple thing, I will explain for only one particular scenario. I have selected this one. What is the meaning of this one? Node 1 is equal to 1. What is the meaning of this one? There is an edge between 0 and 1, which means 1 is adjacent to 0. Now what you have to do? While exploring the node 0, you have to add 1 to the queue. When I will add 1 to the queue, it has to check whether 1 is already visited or not. How will check whether 1 is visited or not? I will go to the node 1, visited array. I will check to the location 1. Yes, it is 0. So I will add it to the queue. So which means that in addition to this particular condition, I have to check with whether visited of I is there or not. If visited is not visited, I can add it into the queue. Okay. Then after dequeuing, this procedure is going to be repeated. Then I will explore. So I think you will do the for 2 also. Am I done? For 0 adjacent nodes are what? 1 and 2. So I have added this also. Right? This particular procedure is going to be repeated to get the BFS out of the given graph. Right? So this is a kind of high level overview of the given code. If you look into the code, you can understand it directly. Right? So try to observe here. I have taken a two-dimensional matrix of size max by max, where max is a constant, and user wish to enter the number of nodes. The number of nodes as n, and then I am supposed to take those number of n nodes graph in the form of an adjacency matrix, where 0 represents for no edge, 1 for the edge. I have read all in the form of two-dimensional arrays, and then you need to have one more input. What is the starting node? What is starting node? Then I am going to call a function called BFS function by passing how many number of nodes are there, what is the graph matrix, and what is the starting node. Now BFS function will calculate all the things for you. Try to observe. Visited matrix, by default what we did, all are 0, means initially all nodes are unvisited. After that I am going to start from a particular node that I have displayed here. Then I made it as a NQ. By default user selected first node will be the added to the queue, NQ, and then I made this as a visited. That is what I explained in the procedure, right? Fine. Next, what I will do, I will try to do the procedure until queue is not empty. Until queue is not empty. So while queue is not empty, I will try to select one node from the queue. What is that one node? Starting node. Starting node, that I will understand it as current node. I will understand it as current node. Then I am trying to print the current node, and I am going to traverse all the columns to identify the respective number of the whether there are edges are there for the respect to current node or not, right? So in the particular scenario, for the 0th row I am iterating graph of current node by I, and the respective node what we are checking is visited or not. Then what I will do, if it is not visited, I will enqueue into the queue and I will make it as a visited. This particular process is going to be repeated, and then finally you will get the solution. Okay, now fine. So here you might think what is NQ and what is DQ, right? This code you already know. NQ means simply a queuing code. If rear is max minus 1, queue is overflowing. If it is minus 1, front equal to 0, and then we are going to add the value into the queue. DQ is something like DQ underflow condition and returning the removing value. Right? While exploring the nodes, you are going to dequeuing and will explore the nodes. And for the emptying condition, you will go this kind of scenario. Right? This is how you can write the BFS code. Right? Anyhow, I will share this code for you. You can execute by yourself. Okay, fine. The next one is a kind of DFS. Right? So for DFS, what you will do? While working with DFS, you are using a data structure called stack data structure, right? Stack data structure is generally used to perform various kind of recursive calls. Am I right or not? Recursive calls or function calls, we can mention them, right? Which means, so while explaining the example also, I have taken the same scenario. I will move on until I complete all the last level nodes. Once last level nodes are completed, I will backtrack, and until the stack is empty. Second, right? While moving on from vertex 1 to vertex something like 3, I will make the earlier node as visited. I will make the present node as visited. I will move on. Right? When I move to vertex 5, I will mark this vertex 5 as what? Again visited, and I will move on. Right? So once the particular level is completely filled, I will backtrack, and suppose for example here it is vertex 7. For vertex 5, the adjacent vertices are like 6 and 7. 6 is completed. If 7 is marked as unvisited, what about actual representation of visited array? Is already visited, making it as visited. So I can mark it as backtrack. So I will backtrack. So this is how you can implement again DFS, which is very easy. You can look into the coding part. So I am just making use of int main, like main method where the program driver is going to start its execution. I am going to ask the user to enter the number of nodes. I am going to take the adjacency matrix, and then I am going to select what is the starting node, and then I am making all the visited nodes as what? 0 by default, and I am going to call the function called DFS function by passing what is the starting node and what is the number of nodes are there. Now DFS function will recursively call it, and while recursively calling, we are making every node what we are visiting as 1, and we will try to check whether it is an adjacent node or not. So this particular highlighted line indicates what? We are selecting a particular edge is equal to 1 or not. If there is an edge, we are trying to check whether it is already visited or not. What is the meaning of 1? There should be an edge, and that edge node is not visited. I will again recursively call for it. That's it. This is how you can write the DFS code. I think we can stop here. So this is all about various kind of graph traversal mechanisms in the